Well, welcome back to a great day. Our focus today is volume of known cross-sections, day 1. So volume of known cross-section is probably the most visual thing we do all year. One word we want to get familiar with is the term slice analysis. Okay, we're going to analyze different slices. So basically what I want you to think of when we're talking about this is what cross-sections are you looking at? So I've got two simple things that you're hopefully familiar with, candy. So if you were to take these Necco wafers and cut them in half or into pieces and then stare at it, what shape would you be staring at? Hopefully you realize you'd be staring at a circle. If I take this piece of candy here and I were to cut it with a knife, just cut it into two pieces, and I stare at it, what shape would I be looking at? And hopefully you would say a triangle. So we have two different slice analyses that we would do, one for a circle, one for a triangle. Let me give you a visual representation of what we're talking about here. So like I said, we're not rotating anything this time. We're literally taking two functions, let's call it my red function and my blue function here, and we're filling it up with a shape. So for example, you can see that I have the square, what I've chosen here. And we've got one square in there. This is telling me the number of squares that I've put in. So I can take this and I can try to show you different views if it will let me. So you can see this view, but I've got one square put in this, in between these two functions. So let me increase the number of squares that I put in. Let's say we put in 16. And I'll kind of spread it across the whole function. So now what we're doing is we're taking that shape and we're filling it up with squares to try to approximate the volume. Now, just like what we've talked about before, the more squares you put in, the more we're going to approximate that volume, and you'll see how it filled that function in closer. And here I can put a maximum of 100 squares in. And again, I'll just kind of show it to you as it moves across what we're doing. So like I said, we're just taking squares and we are filling this shape up with the squares. We are not rotating anything. And again, if I put fewer squares in, you can see maybe a better visual there. But like I said, the more squares you put in, the better approximation we're going to get. So when you get to class tomorrow, if you look around the room, you'll see lots of different projects. So not only can you do squares, you can do triangles, semicircles, you can put any shape you want in there. And our goal is to fill it up to make a three-dimensional shape. So the biggest thing we need to take away from tonight is that volume of a region is not rotated. Okay, we're just filling that region up with a specific shape. So first and foremost, let's star this. We are just going to first find the area by doing a slice analysis and then taking its integral. So again, volume is just the integral of the area of the shape you're talking about. All right, example 1. Let R be the region in the first quadrant below f of x and above g of x from A to B. Find the volume of the solid whose base is region R and whose cross-sections cut by planes perpendicular to the x-axis R, and let's just start with squares. So we're going to start with a slice analysis, and it's actually going to get labeled that way on your paper. Okay, and we're going to first start by drawing the slice in. Notice it's set in the first quadrant, which I have graphed for you, below f of x and above g of x. So here would be f of x, g of x, below f of x, above g of x. I'm just going to draw that slice in. And what you have to picture is this square coming out at you, this three-dimensional square coming out at us. So when we analyze the slice, we're going to start with the area formula for whatever our shape is. So I'm going to use A for area of the square. So the area of a square, so we'll just start with this formula, is length times width, but it's a square, so I'm just going to say side squared. So you're always going to start your analysis with the area formula. Okay, so make a note for yourself. You start with the area formula. Now we'll go ahead and write the area. Okay, it's the length of a side, so actually I'm going to start with my side. My side is my upper minus my lower, so I'm going to call that f of x minus g of x. Now I'm just going to go straight to the area formula. So area is side squared, so I'm just going to take that f of x minus g of x, wrap it up, and square it. Okay, now, volume is simple. Volume, like we've said, is just the integral of area. Area this time happens to be this function right here. So to write my volume formula, I'm just going to move that up. Volume equals the integral of area, which according to this is the integral of f of x minus g of x squared dx. From, I can move to the left from lowercase a to b. And there you have our slice analysis for this square. All right, so let's go ahead and work through this example number 2. So we're given two functions, f of x and g of x, and the question says find the volume of the solid whose base is the region R and whose cross-section is a square. Okay, so I'm going to go ahead and start by graphing these. So y equals 2x just creates a line. If I plug in a 0, I get 0. If I plug in a 1, I get 2. If I plug in a 2, I get 4. So I have just a nice line with a slope of 2. Oops. And then I go ahead and graph 4x minus x squared. So I'm first going to factor to get the zeros. So I pull out x. 4 minus x equals 0. So I get x equals 0 and x equals 4. Okay. I know this creates a parabola facing downwards. I can go ahead and plot some accurate points. At 1 I get 3, at 2 I get 4, at 3 I get 3. And like I said, we know it's a parabola facing downwards. Okay, so my region R, I'm going to lightly shade in, is this section in between the two functions. And I'm going to go ahead and draw my slice in, and I'm going to be perpendicular to the x-axis, which they will always tell us what we're perpendicular to. In this case, I'm just saying we're perpendicular to the x-axis. All right, so like I said, this region R, my cross-section is a square. So every AP teacher in the world is going to call it a slice analysis. Okay, so we'll just label it and we'll go ahead and analyze the slice. So again, volume is just the integral of area. So you always start with the area of the shape it mentioned. Mentioned square, area, side, squared. So now I need to find the length of the side. That's the variable in the problem. So my side is just my upper minus my lower. So I'm saying that's my purple function minus the black function. So I'm going to call that 4x minus x squared. Notice I'm using parentheses in case I have to distribute things, which is most likely the case. So make sure you're always using parentheses. I've got upper minus lower. And now that's the only variable in the function, so I can go ahead and write out my area as, I'm going to call it big bracket for the quantity, 4x minus x squared minus the quantity 2x, and it's all of that squared. So I took my side, and I'm just plugging it into the area formula. And lastly, I just need to find the volume, and like I said, volume is pretty simple. Volume is just the integral of area. So my volume formula is going to be the integral from, I'll get my bounds in a moment, whatever I wrote for area with my dx on there. And of course I got to get where these two things are equal to each other. So again, to find where something's equal, you just set those two functions equal. 4x minus x squared. I'm going to bring these guys over to this side so I get that positive x squared. Subtract my 4x, I get minus 2x. Pull out the x and x minus 2, so I should get from 0 to 2. Now we can go ahead and evaluate that by hand or in the calculator. My goal today is just to set these up. Okay, for our third example, you'll notice I kept the same two functions. I'm just changing the question. Find the volume of a solid whose base is the region R, so make sure you're getting this down, whose cross-section is a rectangle, whose height is 3 times the base. Okay, so we're steering away from the squares and we're talking about a rectangle, so that's the first thing I want you to underline. And here's the description. Whose height is, and again, is in math means equals, whose height is 3 times the base. So if you had to write that out, the height is 3 times the base. Okay, and this time again, our slice analysis is a rectangle. Okay, so let's write the name of the shape down because it's going to change on us. So the question is, what is the area of a rectangle? Okay, some people say length times width, base times height, doesn't really matter what you call it. They talked about the words base and height, so that's what I'm going to use, base and height. Okay, so now there's two variables that have to go in my slice analysis, the b and the h, because those are the two in the problem. If you look back at the square, we said it's just side squared, so I only used s. So this time I'm going to start with the base. The base is, so I'm going to go to that shaded section that we have. I'm going to look at my slice that I drew, my upper minus my lower. My upper's on my purple, my lower is on my black, so I'm going to say that that is 4x minus x squared. Notice I'm in parentheses for each of those terms, minus 2x, upper minus lower. Now the height, remember they gave us the description. They said the height is 3 times the base. So my height is just going to be 3 times whatever I wrote down for base. And notice how I use a lot of nice big brackets to separate things. Parentheses around each of those functions and brackets to separate. Okay, so now we go have that base and the height. We can write our area formula, which is literally my base times my height. So you could write it out twice, and I'll do it the long way for a moment. So that's 4x minus x squared minus 2x, that's my base, I'll put that in a bracket, times my height, which is 3, times the 4x minus x squared minus the 2x. And if I clean that up, which I'm assuming most of you could have done the first time, oops, let me just shift this. I'm going to get area equals this times this, that's just going to be that quantity squared. So I'm going to say 3 times 4x minus x squared minus 2x squared times the 3. And then, of course, to get volume, remember volume is just the integral of area. So I'm going to integrate this function. And again, I'm just slapping the integral around it with my proper bounds and a nice dx on the end. And those bounds went from 0 to 2. All right, in example 4 here again, same functions f of x and g of x. This time we want to find the volume of a solid whose cross-section perpendicular to the x-axis is a semicircle. So that is our keyword, semicircle. So again, it's simply going to start with area. And I'm going to talk about my slice analysis. And let's jot down semicircle for ourselves. All right, so sometimes it's helpful to actually draw the semicircle. The rectangle and square are very simple, but the semicircle, we got to talk ourselves through. So semicircle obviously means half of a circle. So I'm going to start with my area formula. Area equals 1/2 pi r squared. Okay, now I want you to think about this. Watch my slice. I'm going to draw it in the picture. And I want you to picture a semicircle coming out at you. Here's the key on the semicircle. This distance that you drew, what is that of the semicircle? This upper minus this lower. We call that the what of a circle. Hopefully you said it's the diameter. So that's what we need to start with, our diameter here. So I'm going to go back and call it my upper minus my lower. Now I'm going to show you one little trick. If they label these functions as f of x and g of x, it's fair game for you to call them that. I'm not going to write out these functions every time. So my diameter is the parabola, so I'm going to call that g of x minus my lower, which is the f of x. Now here's the thing. I had to start with diameter, but notice diameter is not in the area formula. So now I have to also do radius. Radius is half whatever I wrote for my diameter. So half g of x minus f of x. Okay, so now I'm going to go to the area formula because that was the only variable in there. Area equals 1/2 pi. And now be very careful here. I have to take whatever I wrote for radius and put it inside here and square it. Okay, so there's lots of brackets and parentheses. Be super careful. That quantity squared. Now again, watch my math here. Don't take this for granted. Let's not be sloppy. Inside here, we need to square this amount. So let's start with the 1/2. If you square that, what does that become? I'm going to keep my 1/2 pi. If I square 1/2, I should get 1/4. And then I have this quantity, g of x minus f of x squared. So now when I multiply my coefficients out front, my area is actually 1/8 pi, g of x minus f of x squared. So when I go to slap volume on there, don't forget volume is the integral. We're going to add up all those pieces. That's what an integral does. From 0 to 2 of 1/8 pi g of x minus f of x squared dx. Okay. So again, take your time with that slice analysis in the semicircle. Don't skip steps. All right, let R be the region in the first quadrant under the graph y equals 1 over the square root of x between 4 and 9. Find the volume of the cross-section whose base is the region R and whose cross-section cut by the planes are perpendicular to the x-axis R. And let's go ahead and do squares. All right, so we need to get that function graphed. We have y equals 1 over x. So again, if that freaks you out, you don't know what that looks like, remember, that's okay. Just start plugging numbers in. Now, they particularly want us to look between 4 and 9. So if I plug in a 4, a 5, a 6, a 7, 8, 9, etc. If I plug in a 4, I get 1/2. The rest of these I don't know the square root of, so I'm going to go and plug in then all 9, and I'm going to get a 1/3. So if at 4 I'm at, space this out, that's just my half. And at 9, I'm at a third. Well, how is a third compared to a half? If you cut your pizza in half or you cut it into thirds, is a third smaller or a third bigger? Hopefully you're saying it's smaller, so we know it's going to be below. So this function is going to decrease between those two. All right, so notice it said between the first quadrant under the graph. So because it said first quadrant, I know I'm going to use this axis as the rest of it, and I'm going to go ahead and shade this section in. Okay, then I'm going to draw my slice perpendicular to the x-axis. And I'm just going to talk myself through it. So it said square, so I'm going to go area equals side squared. So all I need to figure out is the side. The side, of course, is the upper minus the lower. So I'm going to go back to this upper, which is on the function 1 over radical x, minus the lower, which is on 0. So you can write minus 0 if it makes you feel better. Clearly, you don't need a minus 0 to that. So then the area, of course, is just side squared. So I'm going to say it's 1 over the square root of x squared. And now I can clean that up because 1 squared is 1, and the square root of x squared, of course, is just x. So my volume, again, is just the integral of whatever I have for area. So 1 over x dx from, in this case, again, you're just saying how far to the left and how far to the right can it go. So it can go from 4 to 9. This is a pretty simple one, so let's go ahead and evaluate this. If I integrate 1 over x, remember you're just saying whose derivative am I staring at? Hopefully that's a no-brainer, and that's the derivative of the ln of x from 4 to 9. So I get the ln of 9 minus the ln of 4. Now, why did I want to talk about this one? Because I just want to refresh log properties with you and where they're going to mess with you. This probably won't be the choice on your exam because subtraction comes from division. So this is equivalent to the ln of 9 over 4. Now, you want to see me get really fancy here. This can get rewritten even further, and this is just I'm kind of having fun with you. Both of these are perfect squares, so I really could say it's the ln of 3 over 2 squared. Would you agree that's 9 over 4? And then they can apply that log property and bring it down in front. So they might, as a choice, call it the ln, 2ln of 3 over 2. But obviously, if it's short answer, this answer is great. And then you just got to keep playing with log properties. Trust yourself and play with the log properties. All right, so let's go ahead and tack the same problem, and we're going to tweak one thing. So this time, again, we're finding the volume of the cross-section who's perpendicular to the x-axis, but this time, our rectangles whose height is 5 times the base. Okay, so I just want to stress that volume is just the integral of area. Okay, so the area changes based off the shape they tell you. So if they name a shape, that's the area formula you want to use. So area equals for a rectangle. So this is my slice analysis. Area equals base times height. Okay, so again, my base is going to be my upper minus my lower in my picture. Draw that slice in, put these big dots to help you identify the upper and the lower. So my base in this case is the upper of 1 over the square root of x minus the lower of 0. My height, that's where this description's coming in. My height is, remember that's h equals, make a little note for yourself, h is 5 times the base. So I'm just going to do 5 times whatever I wrote for base, so 5 times 1 over x. My area then, I've taken care of the 2 letters in the problem. My area is equal to what I wrote for the base times what I wrote for the height. So my question is, what is there 2 of? Do you see 2 5s or 2 1 over radical x's? So I see 5 times 1 over radical x squared. Again, please take note, I'm not squaring the 5. There are not 2 5s. There's 1 5 and then the 2 1 over radical x's. Therefore, volume is just the integral of 5 times 1 over the square root of x squared dx from 4 to 9. And I'm going to go ahead and clean this up. I'm going to say that volume is really 5, pull that 5 out as the coefficient, 4 to 9. When I square that 1 over radical x, I just get 1 over x dx. So this integral, like I said, is very simple. I'm going to get 5. When I integrate 1 over x, that's really the ln, upper minus lower. The ln of 9 minus the ln of 4, and it's 5 times that quantity. So just like the previous example, they can start messing around with the log properties with you. So again, I'm going to turn this into division. So it's the ln of 9 over 4 times 5. Again, they could play around making, that the 3 and a 2 and calling it squared and bringing the 2 down in front. So that could also be 2 ln of 3 over 2. But again, if it's multiple choice, they'll probably mess around with you. If it's short answer, this answer is great just right here. All right, let's go one last examples. So again, same picture, same functions. This time we're just changing the cross section, still perpendicular to the x-axis, so life is good. But we're going to attack the semicircles, which might be the toughest. And the semicircles, I always draw the picture for myself. Okay, so I'm picturing the semicircle coming out at me. And the reason I draw it is because I have to remind myself that this distance, this upper minus lower, is not the radius. It's actually the diameter of the circle. So area of a semicircle is 1/2 pi r squared. So I'm thinking the only variable I need is the r, but I have to, like I said, be careful that this distance in here is actually the diameter. So I'm going to start with diameter. So my upper minus lower, my 1 over radical x minus 0 is my diameter. Therefore, my radius is half of that. So 1/2, 1 over radical x. My area then is 1/2 pi. Now it's whatever I put for radius, I have to square. So I'm going to say that's 1 over 2 radical x squared. Okay, so notice I'm taking whatever I put for radius in parentheses and squaring it. So my volume is just the integral of whatever I put for area. So that's 1/2 pi times 1 over 2 radical x squared. And again, that goes from 4 to 9. Okay, now if this is calculator active, please don't waste your time trying to multiply anything, clean it up. The calculator is going to do all the work for you. If it's, you have to work it out by hand, I am going to clean it up slightly, and I will kind of talk through that this time to make sure we're on the same page. So I'm going to take this quantity and square it. I have to square everything inside there. So I've got from 4 to 9, I've got this 1/2 pi, and I'm just going to do it in baby steps here. When it's obviously nothing needs to get FOILed, there's no plus or minus, I'm just going to square everybody. The 1 becomes a 1, the 2 becomes a 4, and the square root becomes just x. And then when I clean up these, I'm going to get volume equals, I'm going to get a 1/8 and a pi, and a 1 over x from 4 to 9 dx. So where did that come from? Well, a 1/2 times a 4th gets me the 1/8. I've got the pi and the 1 over x. So integrating is actually simple. I can pull out the 1/8 pi, and then I'll integrate the 1 over x. So that's the ln of 9 minus the ln of 4 times that 1 over 8 pi. Well, I think that does it for tonight, and we'll get some great practice with these 3 shapes. See you tomorrow.